So welcome to the 54th lecture of surface engineering. We have now started discussing generation from all the way generation to various scopes of application of laser for material processing as well as surface engineering. So in the previous lecture we discussed how do we generate laser, what are the various characteristic features of the laser, what are the material properties which actually determine the level of heating and how does heat propagate in the solid, and what kind of various forms of processing we can do, particularly for engineering applications, what are the two main parameters that we vary to generate different levels of heating in the solid, and eventually we can make use of that heating for various kinds of change of shape, change of dimension, change of or joining of solids, and surface engineering, of course. Now, having understood these fundamentals of laser material processing, we would now like to concentrate on the various types of processes that we can do using laser. So in this part B. So the first and foremost is material removal. I told you that by proper combination of interaction time and incident power density, if you have very high power density and applied for a very short period of time, then the heating effect will be completely confined to a very small volume, and in the process, in this short period of time and in the small volume, temperature will not only cross the melting but even vaporization temperature. So when it crosses the vaporization temperature, then obviously you actually will convert the solid immediately into vapor. Now this can be done purely by heating process, or in some cases with certain shroud gases, but in some cases you can use an active carrier gas which could be oxygen. So during heating it will also allow oxidation, and in the process it will vaporize very easily. So what you need is an incoming laser, and there are two possible strategies. One is the transmissive optics, the other one is reflective optics. So you'll have a laser beam which will be incident onto the solid. So this is the solid that we are irradiating with the laser beam, and the beam comes with through a nozzle, and there could be a flow of gas, either a shroud gas or an active gas like oxygen surrounding this laser, and when the beam interacts with the solid, it actually can create immediate vaporization, and depending on the interaction time, the depth of cut will be determined, and there has to be a relative motion. Either the solid moves or the laser beam itself with the nozzle it moves. So we should create a relative motion, and so just like this view graph here, you can see that immediately. So you create, you sputter actually droplets, and these droplets fly off. In the process they also get oxidized. So you see just like what we see in the days of Diwali, so you also see such sparks flying all over. But the interaction is on a very small line, and as a result, so for example, here is a line that you can see is defined by this cut. So by way of machining, we mean cutting and drilling, marking or scribing definite. You can etch out a name or a design, or cut exactly according to the design. You can do cleaning and polishing, removal of controlled depth of material. You can do patterning or texturing, and you can also remove from the surface patina or certain layer which is unwanted. The process is desirable because it's very fast and completely automated. There is no manual operation involved in particularly this kind of a cases. So the specimen is not destroyed. There is no also immediate, a lot of the wastage is minimal. Then it is very versatile, and any material, practically any solid can be machined using laser, and there is very little or negligible amount of heat affected zone. So machining, particularly since we are talking about a beam, and we can not only control the intensity and the interaction time, we can also control the shape and the size and the focus of the beam. Now, one other important thing we'll soon discover, particularly with regard to joining operations, is that the focus of the laser beam with respect to the surface determines what is the power level that is delivered at that point of time. So we can actually create a very sharply focused beam and make it extremely fine, so fine as finer than, let's say, 10 micrometer. So depending upon the size of the beam, we can create features which are easily few tens of a micrometer. So if this length scale is 100 micrometer here, then we are talking about features which are created and depth wise several hundred micrometers, so maybe almost like half a millimeter depth of cut, and such sharp and completely smooth vertical wall of cut. And these the diameter of these holes could be easily some 20-30 micrometer. So extremely fine size. So these micromachining features can be also not only completely vertical, can also be inclined. So actually one can start by drilling a hole, rectangular or square hole at the very bottom like this, and then in order to reach there, you actually can have various cuts with various widths. So essentially you can create a step-like structure and with very precise geometry using laser. You can have, likewise you can create these very specific drilled holes of certain dimensions, and the wall, inner wall actually need not be vertical, it can be inclined. So you can make certain holes which are having inclined surfaces. One can also create such heat pipes or heat sinks or certain features which will expose very high surface area for heat dissipation. Even can make such heat dissipation devices or heat exchangers where because of the sharp features, any gas that passes through our air will have will actually be able to throw away heat much more efficiently through this kind of structures than in a otherwise solid structure. So the same micromachining patterns could be done on steel, on semiconductors, on polymers, on any solids, and with very large aspect ratio like this nanopillars of carbon nanotube. Or you can drill holes on a silicon wafer, maybe a few, almost half a millimeter or so deep, or you can create channels and vias and various other structures of very specific dimension. That can be done very easily on laser, on metallic surface. So here is an example from a commercial house that you can create so many markings, so many types of marking. You can literally create different markings and scribings on metallic surface. You can even bring in colors by way of controlled oxidation. So various forms of color tinting possible by exposing a certain amount of gas and controlling the interaction time and power. So the depth of the oxide layer that you create will actually determine what would be the color on the surface. And of course, the basic composition of the substrate is important. Similarly, we can make such cooling channels, microfluidic cooling channels on either on a semiconductor device or on metallic heat exchanger devices. And this could be a stainless steel or nickel-based invar alloys, titanium, aluminum, polymers like polyamide, polycarbonate, and other forms of commercial plastics and polymers. Now, laser can also be an extremely precise tool for cleaning or finishing. As I said, since the beam can be focused, can be shaped and focused such a way that the diameter or at the focal point, the diameter could be just a few micrometer, as sharp as small as that. And also you can deliver power in such a controlled manner that you not only heat, you actually vaporize a very thin layer up to a depth of, let's say, 10 nanometer or maybe 5 nanometer and not 1 nanometer more. So that means it can be that precise. And as a result of that, one can actually clean the surfaces of human teeth to such metallic molds or glass objects or various solid surfaces. And you can easily make out the difference of these. Even surface topography can be made very smooth. So this kind of a surface, a rough surface, can be made very, very smooth by such laser assisted surface finishing. And these kind of surface asperities can be very easily handled by controlled removal of material from the surface. Now, after these controlled cleaning or finishing operations, let me take another very interesting example. You know, the very priceless art objects, paintings or sculptures, if they have to be cleaned, you cannot afford to do that cleaning by physical means. You cannot allow a cleaner to scrub the paintings of, say, the priceless Mona Lisa or a sculpture of Michelangelo or somewhat like that. So in that case, you actually are allowed to touch those only if you promise that you are going to remove maybe 5 nanometer or 6 nanometer and not 8 nanometer from the surface. And those objects develop certain rust or certain chemical coating over a period of time by way of interacting with atmosphere. You know, some kind of sulfide or some carbonate or some layers can form which actually cause discoloration. So you got to remove those compound layers, complex compound layers, by the only way you can do. You can't even use a soap solution because that will react and make a different kind of a color. So the only way is to remove the oxide layer or the reaction layer from the surface by way of vaporization. And laser can do that very, very precisely. So indeed, laser is used for cleaning priceless art objects. Another form of material processing could be sintering. So you actually, when you are dealing with powders or small objects, I mean particulates, you need to sinter them, join them together. So usually this could be, let's say, powder masses of various either similar size or various size. So you can have small or big and so on, all kinds of possibilities. So joining will essentially depend upon creation of temporary diffusion bond here, so that electrons can flow across. So if we are talking about metals, then obviously we want some kind of metallic bond to be formed at this, which could be due to melting or due to purely solid state diffusion. So if you are heating a bulk like this up to a certain depth from the surface, so you can do layer by layer, or you can do in a controlled manner such a way that you heat up to an extent so that the surface sees the highest temperature. So the heating effect will be maximum at the surface, and hence the powder particles will actually get heated up such a way that a thin layer from the surface reaches fairly high temperature that will allow diffusional bonding to form. So it can be solid state, it can be also formation of thin molten layer, and so liquid phase sintering, and this thin layer may form because of certain reaction, eutectic reaction at the surface. So no matter what, actually using laser, one can actually start with powder particles and then sinter and create a base, a bulk solid, the density of which could be close to the theoretical density. There is always a possibility of retaining some of the porosities, and one can actually create a very good routine for sintering to avoid such retention of porosities. Another very major application is joining. Now, joining not only of similar type, where so there are three possibilities actually one can think of. If we want to join a solid body A and B together, we can simply heat here such a way that this part melts and some part of the B melts, and eventually they fuse with each other. So it's a fusion joint created by partial melting of A and B at the edges. So that's typically welding. But you may also do soldering or brazing, whereby you have A and B as two parts, and then you bring in a filler metal and use the laser beam to hit the filler metal so that the filler metal melts and allows droplets to trickle in and eventually fill up this gap in between. So when this liquid fills up the gap, this liquid actually wets with this solid A and B well, and in the process can create a very good soldered or brazed joint. If the temperature is higher, you call it brazing, typically used for copper alloys, or you can do soldering, typically for metal to semiconductor or semiconductor to semiconductor joining. Let's say easily below 300-400 degrees centigrade. So roughly speaking, about 400-450 is a cutoff point. Anything joined below that is called soldering, and anything above is brazing, provided you are using a filler metal, a low melting eutectic composition which fills up the gap. But if the joining process requires melting or fusing the edges of the two solid pieces without necessarily requiring a filler metal, you call it welding. And all these welding, brazing, joining, all these can be done easily with laser. So here is a process chart in terms of the beam quality and the power that you're delivering, and that allows you to do various kinds of joining activities. The for joining, we already discussed while discussing electron beam assisted joining that if, so here is the importance of locating or the location of the, so if this is the solid we are talking about, and so we have three possibilities. We have the possibility of the focus resting above the surface, we have the possibility of the focus coinciding with the surface, or the focus going below the surface. So if it is above the surface, then the effect of heating will be shallow, will be fairly shallow and diffused. So you end up getting a conduction melt pool. If the focus is coinciding with the surface, or in particular is below the surface, in both the cases you actually can see heating profile which will be fairly deep penetrating type. And that's the typical keyhole type of joining possible when particularly when the focus is below the surface. But nevertheless, one must admit that the advantage of using laser-based welding is that you can do it in air. One of the biggest advantage of laser material processing is that you can do either in controlled atmosphere in confined chamber, or if it's a non-reactive metal, you can easily do everything in open air. And you can do processing where you actually have a very high melting on one side and low melting on the other side. So you have to have a correct strategy of joining them. But you can certainly use laser for joining. The advantage electron beam enjoys over laser is in terms of its deposition profile, which is Gaussian. So the peak is below the surface. So you actually can make this kind of a deep penetration joining better with electron beam than with laser. But on the other hand, with laser you actually, and there are other difficulties with electron beam, that it has to be done in a confined chamber at very high vacuum. So you have limitations in terms of size and dimension of the component that you can handle, whereas laser can actually do the processing entirely in open air. With laser, you actually can select a certain wavelength which will penetrate through, pass through, or transmit through one solid on the top without creating any heating effect until the time it actually interacts with the other solid at the bottom, and that's where it can get absorbed. So if I have two materials A and B, where A is transparent and B is translucent or absorbent, then I can create a situation where, and I can actually join the interface. So this interface can be actually welded or joined by way of laser heating, purely because of the fact that the laser beam is transparent to A but absorbent to B. So beam passes through without heating through A, but heats only when it interacts, or only when it is at the interface between A and B. And B gets heated up, B melts, and that's when heat transmits upward and then part of A melts, and then you form a joint. So this allows various types of very specialized joining for automobiles, for spectacle glasses, polymeric substances, particularly the transparent ones, and various types of applications in automobiles possible, also for plastic windows and cards and so on. Now, this is just an example as to how this could be very, very useful. One last thing that I would like to mention is the possibility of using laser for building a solid component, three-dimensional solid component, layer by layer. So here are two cases of, if this is the prototype, then I can actually build this complicated shape, or even this one, by additive manufacturing process. So additive manufacturing would mean that let's say you want to create this conical shape. So you would feed in powder here, and here is your laser beam. So, and this is my stage. So in the first case, I'll allow a circular motion of the beam or the stage, in this case maybe the beam, and the powder hopper. So the beam interacts here and the powder comes and hits here. So you melt the powder and you deposit the molten powder at this point. And then the beam and the powder, they move away, and when they move away they go to the next spot and again deposits another layer. So likewise, if I make a circular motion, then I'll create one circular section like this of a particular powder coming from top. And of course, I have my ability to control not only the precise diameter or the shape, circular shape, but also the height of the shape. So I build up, in the first layer, I build up only up to this depth. So this is one circular section that I have created. The next time I reduce the diameter of this, I describe a smaller diameter circle. And so now I create another one which is shorter. Next time, even smaller diameter, even smaller diameter. So when these are done not on the same level but at progressively higher and higher level, so effectively I should be able to create one layer like this here, the next layer like this here, the next layer like this and like this. And if these are all circular sections, so essentially I'll end up making a cone out of it, a circular conical shape like this. So this is just an example of a simple geometry. But if I want a more complex geometry like this, so I can do that, and I can also create a more complex shape like this, or any shape for that matter, I can do gradually by feeding the powder and combining the laser such a way that the powder is melted in flight and then deposited. And I change the vertical height of this deposition so that I can create a not just two-dimension. So I convert two-dimensional first layer into three-dimensional bulk component. It can be hollow, it can be solid, it can be semi-solid, it can leave control porosity, control diameter inside, volume, open volume inside, and all kinds of possibilities. So essentially, it all depends upon, so I can create even controlled holes, controlled porosities, and I can change the angle. I can build a layer with a curved surface, not necessarily a flat surface. I can make a vertical, I can make inclined. So all these processes are possible by an additive way. So I add on layer by layer. I add one layer to the next layer to the next layer. So when I go from one layer to the next layer, I can change the diameter, the dimension, the thickness, the inclination, the shape. All those possibilities exist. So in principle, I, instead of actually creating, processing the material or manufacturing the component in a bulk manner, where I create an ingot, then I forge, I roll, I do machining, I do extrusion, I do all kinds of material processing for the bulk. Instead of doing all those laborious and time consuming and energy intensive processes, I can simply use a powder feed and a source of heating through laser, and I can build the final component in one shot, one single manufacturing stage. So that's the advantage and beauty of additive manufacturing. And additive manufacturing, by the way, is nothing different than a very simple surface engineering approach called cladding. So in case of cladding, you simply have a substrate on which you deposit a new layer. And here you may or may not have a substrate, but what is important is you deposit not just one layer, you deposit multiple layers, so that cumulative way it actually can build a complete structure, a complete solid. So this allows actually elimination of lot of time, energy, material cost, and various other advantages. So that's why direct manufacturing, particularly using laser, is the most talked about manufacturing approach of present time. And that's possible because laser gives you practically immense flexibility and uniqueness in its approach, which is not possible with other types of tools. So there are many methods available. I just took the liberty of picking up some of them from the published sources and list them out here. So depending on the approach, some of these are called selective laser sintering or direct metal laser sintering. So in selective sintering, you'll use a laser to sinter the powder feed that you feed in up to a certain depth, and the powder themselves will have certain binder coating on it. So when you heat, these binders melt and they fuse and they bond with each other. In case of direct metal laser sintering, you actually use, so in one case you have two particles with certain coating on top, and the coating fuses easily and binds. On the other hand, in direct metal laser sintering, you have two metal powders and then they can actually fuse by a typical welding process. You can have even selective melting. Instead of solid state sintering, you can have selective melting. What happens here? You can do, instead of laser, you can do it with electron beam melting. You can do what is very popularly known as 3D printing. So like, for example, you print the alphabet A with certain thickness, dimension, and shape, and so on. So you can also use a powder feed to create this kind of a shape or a geometry, and you can effectively create an A out of only powder. Now, usually the powder feed and the laser can be different, coming from different directions, but in principle or in reality even, it's also possible that you have a laser beam coming through a particular nozzle, and you have concentric feeder or hopper around them, which can feed one single or multiple powder. So if the laser beam is incident here, the powder can also come in a concentric manner to the same focal spot. So this is a lot better than having laser and powder coming from two different directions. So this is fairly possible. In fact, these days with a fiber laser delivery system, this kind of a possibility has become extremely feasible. And to make things even more flexible and even more exciting, now actually the whole laser delivery system with the fiber laser can be loaded on the arm of a robo. And the robo can perform not only X, Y, or Z directional movement, it can also rotate in certain angle. So basically, a robo arm can define exactly like a human arm, can actually define any shape or any size. So with this possibility, the arm can actually rotate, it can move, and it can translate and create. So essentially, this robo arm will carry the laser beam, the powder feeding system, the nozzle, concentric nozzle, and then both will act simultaneously. And now if it goes through a circular motion or vertical motion or lateral motion in X and Y direction, can create practically any shape. So it's almost like an artisan moving his hand with clay and then making a three-dimensional shape. So instead of printing letter A on a two-dimensional sheet, you actually can go layer by layer and then print an A which is not only a two-dimensional but three-dimensional. So that's 3D printing. So you can also use multi-phase jet solidification. You can have multiple jets falling onto the surface. You can do extrusion and deposition of semi-solid metals and then create a final shape. Or you can have a powder bed and you can do direct metal deposition or laser engineered net shaping. In both the cases, you can create a complex shape which you have to define beforehand using a computer-aided design mechanism. These are various names possible. Essentially, if you are feeding powder or wire or tape or rod, in all these cases, that's the feed side, that's the material side, and it can be one material, it can be multiple material with multiple feeding points, or multiple materials with a prefabrication process bonded in the form of a wire or a tape, which is not material A alone, but A plus B or A plus B plus C in various volume fractions, in varying volume fractions, and so on. So that's how the material feed can be changed, and material feed can define what material, what geometry, what composition, and what gradation, and so on you will ultimately develop. And by controlling the laser and its power, you actually can make it melt, you can make it clad or deposit, and make it a very firm and a dense structure. You can even create a lot of gradation in terms of thickness, in terms of shape, in terms of porosity or other physical or chemical parameters. So you actually, the possibility is literally infinite. You actually can do complete engineering of finished component development, manufacturing, using a single tool of laser with a powder feeder or a wire feed or some other material feeding system. But this is very much in its infancy. It's in the nascent state. Nobody can claim that tomorrow itself I am going to build a complete engine block using direct manufacturing, laser-based direct manufacturing, because it has to go through various forms of testing, characterization, certification. Then only you'll have the reliability. Then we'll earn the confidence of the users or the customers. But this opens up an excellent possibility of going into a new direction altogether, where manufacturing would be not only easier, will be much more versatile and faster, and will open up new possibilities which even today is not possible. So by way of recapitulation, I would say that we can classify the material processing into four major groups of removal, machining, addition or shape changes and so on. Various forms of manufacturing, or we can do joining, similar or dissimilar, same thickness, different thickness, same composition, different composition, or we can do surface engineering. So these are the four major possibilities: forming, machining, joining, surface engineering. The main process parameters remain the interaction time and power density, the focal point, and so on. The micro machining is very possible because the shape of the beam can be not only of the micrometer size, but also the heat deposition profile will be so precise and reproducible that's not possible in any other form of heating. And it's a very, very transient process. At a time, you are heating only a small volume of the bulk, and rest of the bulk, so only 1% or less is heated up. And that heating can take it to the vaporization temperature, whereas the 99% can remain at room temperature. So that adds to the various possibilities which otherwise is not feasible in conventional processing. So using the same laser, actually by changing the parameter, the power density and the interaction time, you can do either only heating, you can do sintering for that matter, you can do melting, solidification, you can do even machining with or without carrier gas like oxygen. The surface condition is very important in terms of efficiency of coupling the laser matter, and also the wavelength, the various material properties like the density, the melting temperature, the specific heat, and so on and so forth are also very important. We saw that using laser we can do all kinds of joining processes, welding, brazing, soldering, and using laser this joining processes are so easy because I can do it in air, and I can do it for dissimilar things, and I can do it such joining processes even for non-conducting materials, non-electrical conducting, and so on. So I can try and join even an insulator with a metal. Laser sintering is a bit of a problematic, particularly when you are dealing with the dissimilar sizes or dissimilar composition, and that's purely because at a time you are heating only the surfaces of the powder particles and not its entire bulk. But one can actually use laser sintering in combination with application of pressure and then make a denser and a more stronger compact or sintered product. Additive manufacturing is a very, very exciting process, and cladding can be a precursor, but essentially additive manufacturing opens up completely new possibilities of producing finished component of very, very complex shape, size, contour, and geometry, only starting from powder and building layer by layer. So the different laser assisted manufacturing processes all can be treated with the same setup, same machine, and can be used to build up various kinds of manufacturing, can be used to conduct various kinds of manufacturing practices. And laser is certainly one of the most versatile tools for such applications. So in the next few lectures, we'll discuss about various surface engineering processes. Though the course is about surface engineering for wear and corrosion resistance, but in the last couple of lectures, I thought it would be prudent to discuss various manufacturing processes possible using laser as a non-contact tool. Right. Thank you very much, and we'll move forward now for surface engineering.